Hello, in this video we're going to be talking about Euclidean and metric spaces. Now while all Euclidean spaces are metric spaces, Euclidean spaces are a little bit easier to think about. So we're going to introduce Euclidean spaces first. So let's define what a Euclidean space is. So in order to do that, we're going to have to talk a little bit about some prerequisites, and then at the end we can conclude and define fully what a Euclidean space is. So if we let k be a positive integer, we can define r to the k to be the set of all ordered k tuples, and we'll label each element x as x with a little arrow above it. And so x is going to be equal to x1, x2, all the way up to xk, where each xi from I equals 1 all the way up to k is called a coordinate, and it's a real number. And each x with a little arrow above it is called a point or a vector. So vectors are part of a structure called a vector space. So let's go ahead and define what a vector space is. So a vector space is a structure where the elements are called vectors and constants that are multiplying the vectors are called scalars. In the sense of RK, they're always real scalars, but if we were to have maybe CK as a vector space, they would be complex numbers or something like that. But vector spaces are always structures over a field. So in our case, our field is going to be the real numbers. So the first property is associativity. If you don't remember what associativity is, I'm going to write it down below, but most of these properties you can go back to the video on groups and refresh yourself. So the first property is associativity. The second is commutativity. Next, we have to make sure there's the zero vector, or the additive identity element. We have to also make sure that there are inverse elements. So vector spaces themselves are abelian groups with respect to addition. Now they also have this additional structure where they can be multiplied by scalars. So there has to be compatibility between scalar multiplication and the vectors. So if I have a times bv, or bu in our case, that's the same as ab times u. The identity element in our field works the exact same way it would normally. So 1 times a vector is the vector, and the vectors distribute with scalars. So a times u plus v is au plus av, and for two real numbers, a and b, a plus bv is av. There are also other things that we can put on this space. For instance, we can have the inner product, or what's also sometimes called the scalar product or dot product. And all we do is we multiply the first coordinates of our two vectors, and then our second coordinates and our third coordinates and so on, and then we add them all together. And we can also put a norm on this set, or on this space. And when we put a norm on the space, the norm of x is x dot x, so it's the inner product of itself square rooted. So it's the sum of each coordinate squared, and you take the square root once you're done with it. So the vector space Rk, with this inner product and norm as defined above, is a Euclidean space. And Euclidean spaces have their whole own set of properties. The first thing about a Euclidean space is that the norm of any vector is always greater than or equal to 0. Next, if it is equal to 0, then our vector is actually the 0 vector. Next, if we have a scalar times a vector, and we take its magnitude, we can just pull that scalar out through an absolute value. So the magnitude of alpha x is actually equal to the absolute value of alpha times the magnitude of x. The next three give us inequalities for the relations of inner products and sums. So if I have x dot y and we take its magnitude, that's less than or equal to the magnitude of x times the magnitude of y. And if I have the sum of two vectors, so x plus y, and I take its magnitude, it's less than or equal to the magnitude of x plus the magnitude of y. And finally, we have our triangle inequality. So if I take two vectors x and z, and any other vector y, the magnitude of x minus z is less than or equal to the magnitude of x minus y plus the magnitude of y minus z. And a final note about Euclidean spaces, as stated before, all Euclidean spaces are metric spaces. So before we go ahead and end on Euclidean spaces, we're just going to transition in, and we're going to have to define what a metric space is before this note makes sense. But in order to talk about what a metric space actually is, we have to talk about what a metric is. So given any set x, a metric is a function, we'll normally call it d, historically for distance, from two elements in the set, so x cross x, into the reals. And this is true. This function d is a metric if and only if I have the distance between x and y, it's greater than or equal to 0. And the distance between x and y is 0 if and only if x and y are the same point. The third says it doesn't matter what order we take the distance in. The distance between x and y is the same as the distance between y and x, right? If I'm going to the grocery store, it doesn't matter if I walk there or walk back. I'm both walking the same distance. And finally, we have our triangle inequality, which says that the distance between x and z is the distance between x and y plus the distance between y and z. And that's true for any y in our set. Now, if d is in fact a metric for x, then the ordered pair xd is a metric space, just like how if tau was a topology for x, the ordered pair x tau would be a topological space. So to wrap things up, let's look at a couple of examples of metric spaces. So our first example is Euclidean metric. It's the Euclidean space itself, Rn. Okay. Our second example is going to be essentially the Euclidean metric in the one-dimensional space R1. And that's just defined by the absolute value of x minus y. Next, we're going to look at the discrete metric. So it's called the discrete metric because if we look at the topology that's created by the metric space, it ends up being the discrete topology. And that's defined as the distance between x and y. We just do a quick check. Is x equal to y? If yes, then it's 0. If they're not equal, we assign the distance to be 1. And our final example comes in 3 parts. So we're going to set our set equal to R2, the real plane, and we're going to just define x and y explicitly. So x is the ordered pair x1, x2, and y is the ordered pair y1, y2. So our first distance is our Euclidean metric, the square root of the sums of the differences, as we're familiar with. Our second one is going to be the absolute value of x1 minus y2, or x1 minus x2, and then y1 minus y2. And in our second metric, we add them together, and that gives us a metric. And in our final example, instead of adding them together, we just look at which one's the biggest, and that also defines a metric. Thank you all for watching.